Hello everyone, welcome back to the channel. Today we are diving into something that might seem simple but is absolutely crucial for getting the best result from your GC and GCMS analysis. That is, carrier gas selection and its optimization. So whether you're a student learning chromatography or a lab professional looking to optimize your method, understanding how carrier gases affect your separation efficiency can make the difference between mediocre and excellent result. So we'll be covering three main topics today. The different carrier gases available and their properties, how to choose the right carrier gas for your application, the Van Deemter equation and what it tells us about the optimization. So let's get started. There are three gases that is available for us, that is helium, hydrogen and nitrogen. So helium has traditionally been the most popular choice, especially in US. It's inert, safe and provides excellent separation efficiency. However, there's a big problem. Helium is becoming increasingly expensive and has supply chain issues. We are literally running out of affordable helium. While on the other hand, hydrogen is gaining popularity as a helium alternative. It is most efficient carrier gas, meaning you get the best separation at higher flow rates. It's also cheap and readily available from generators. The main concern is safety. Hydrogen is flammable, but modern GC systems have excellent safety features, and when used properly with a hydrogen generator, it is quite safe. Now coming to a third gas, that is nitrogen. Nitrogen is most economical option. It's abundant, inexpensive, and completely safe. So what is the downside? It's less efficient than helium or hydrogen, which means you need longer analysis time or you have to sacrifice some separation quality. Each gas has a different optimal linear velocity, which we'll discuss more when we get to the Van Deemter equation. So how do you choose your carrier gas? So let's look at the key factors. First one is separation efficiency. This is where the Van Deemter equation comes in, which we'll cover in detail shortly. Now hydrogen gives the best efficiency at higher flow rates. Helium is excellent across a broad range and nitrogen is adequate but requires optimization. Second factor is cost and availability. With helium prices skyrocketing and supply uncertain, many labs are switching to hydrogen generators. The initial investment pays for itself quickly. Nitrogen is cheapest if you have a building supply or a generator. Third one is detector compatibility. Now this is crucial. For FID and TCD, all three gases work fine. For mass spectrometry, helium and hydrogen are preferred because they are easily pumped away. Nitrogen can be used with MS but may require different vacuum pump configurations. Fourth, let's talk about safety considerations. Hydrogen requires proper safety protocols, leak detection and staff training. But remember, the hydrogen flow rates we use in GC are quite low and modern systems have multiple safety interlocks. Now coming to the fifth factor, that is analysis time requirement. If you need fast analysis, hydrogen allows you to run at higher flow rates without losing efficiency. Nitrogen typically requires slower flow rate for optimal resolution. So here's a quick pro tip. If you're switching carrier gases, you'll need to re-optimize your method. So don't just change the gas and expect the same result. Now let's get into the science with the Van Deemter equation. This is the mathematical relationship that describes how efficiently your column separates compounds. So the equation is H is equal to A plus B slash U plus CU, where H is the height equivalent to a theoretical plate, basically a measure of peak broadening. Smaller h means better efficiency and sharper peaks. And u is the linear velocity of the carrier gas. So let's break down each term. So as I told you all, h is the height equivalent to the theoretical plate and u is the linear velocity of carrier gas. Now the A term represents the eddy, diffusion or multiple path effect. So as the carrier gas molecules travel through the packed column or round the stationary phase in capillary columns, they take different paths. Some paths are longer, some shorter, leading to band broadening. The A term is independent of flow rate. So it's a constant horizontal line on the Van Deemter plot. Now coming to Bu term, it represents the longitudinal diffusion. This is the natural tendency of your analyte molecules to diffuse along the concentration gradient in the column. The longer they spend the time in the column, meaning the slower the flow rate, the more time they have to diffuse and the broader your peak becomes. That's why this term is inversely proportional to velocity. At high flow rates, there's less time for diffusion, so this effect is minimal. Now coming to Cu term, this represents mass transfer resistance. This is about how quickly your analyte molecules can equilibrate between the mobile phase and stationary phase. At higher flow rates, molecules don't have enough time to fully partition in and out of the stationary phase, leading to band broadening. This term increases linearly with velocity. So when you plot these three terms together, you get the characteristic Wien-Deemter curve, a U-shaped curve. The bottom U is your optimal linear velocity where h is minimized and efficiency is maximized. Here's where the carrier gas choice becomes critical. Different gases have different Van Deemter curves. Now hydrogen, it has a very flat curve, meaning it maintains good efficiency over a wide range of flow rates, especially at higher velocity. That is why hydrogen is excellent. Helium has a similar but slightly less flat, still very good across a broad range. Now talking about nitrogen, it has a much sharper curve with a more pronounced minimum. This means you need to operate closer to the optimal velocity, and if you increase the flow rate too much, you'll see a significant loss in the efficiency. So the optimal linear velocities are, for hydrogen it is 40 to 50 centimeter per second, helium it is 30 to 40 centimeter per second, for nitrogen it is 20 to 30 centimeter per second. So this is a comparison of the runtime where different carrier gases were used for same analysis. So when nitrogen gas was used, the velocity was 12 centimeter per second at 80 degrees Celsius and the flow rate was 0.2 ml per minute. That was constant. So the runtime was 48.5 minutes, whereas for helium it took only 19 minutes and for hydrogen it took only 13 minutes. So how do you actually optimize your carrier gas flow in practice? So step 1 would be determine your optimal linear velocity based on the Van Deemter curve for your carrier gas and column. Most column manufacturers provide this data, or you can measure it experimentally. Second is calculating the required flow rate. Remember, linear velocity and volumetric flow rate are different. The flow rate depends on your column dimensions. Most GC software can calculate this for you. Now the third step is consider your analysis priorities. If you need maximum resolution and have time, operate at optimal velocity, the bottom of the Van Deemter curve. If speed is critical and you're using hydrogen, you can operate at higher velocity with minimal efficiency loss. And step 4 is verify your result. Inject a text mixture and calculate parameters like resolution, theoretical plates, and peak symmetry. Adjust if needed. Let me give you a real world example. Let's say you're switching from helium to hydrogen to save cost. So your optimal linear velocity changes from 35 cm per second to 45 cm per second. This means you can actually run your analysis faster with hydrogen while maintaining or even improving separation efficiency. So your 20-minute helium method might become only 15-minute hydrogen method with better peaks. Now, one important consideration for GCMS users. When switching carrier gases, you may need to adjust your MS vacuum system setting. Hydrogen is lighter and pumped more efficiently than helium, which can actually be an advantage. So let's wrap this up with some key takeaways. First is carrier gas selection matters for efficiency, cost, and analysis time. Second is hydrogen is emerging as a top choice due to helium shortages. It's efficient, economical, and safe when handled properly. Third, the Van Deemter equation explains why different gases perform differently at various flow rate. Fourth, each gas has an optimal linear velocity and operating at or near this velocity maximizes your separation efficiency. The last one is method reoptimization is essential when changing carrier gases. So the bottom line, understanding carrier gas selection and the Van Deemter equation empowers you to make informed decision and get the best performance from your GC or GCMS system. So if you found this video helpful, please give it a thumbs up and subscribe for more analytical chemistry content. Drop a comment below if you have any questions about carrier gas optimization or if there are other GC topics you'd like me to cover. Thank you for watching and I'll see you in the next video.